I want to thank the organizer for this opportunity to speak this workshop. And also, I wanted to give my apology in advance because it's going to be a bit more theory-heavy talk with respect to the others that have been today. So I don't know if someone's happy about it or not. Okay, so yeah, the title is Oddities in the Entanglement Scheme Quantum Six-Vertex Model. So basically it's about finite size effects that happen in entanglement in a class of two-dimensional critical wave function. And this was a work done with Jesus, which is a PhD here, Enrique, which is now at CERN, and also Germán Sierra. Okay, so a bit of a strong start. So I said that it is about entanglement in a class of critical wave function. So what kind of critical phases we are talking about here? We are talking about two-dimensional quantum system, and we are talking about critical points that separate topological order states from normally order state or symmetry broken states. So these are obviously, and at the critical point you have a scale invariant physics. But the particularity that's happening for this class of critical points in two dimension that not only like the action or the dynamics is scale invariant, but also the ground state in space is a scale invariant. So this let us like relate the basically observable at the same times, like observable at the same times to observable in conformal field theory. And what are the kind of wave function that we are considering in this model? So we are starting from a Hilbert space where the allowed states are basically labeled by the, we can call it like the microstate of a classical model. So the type of classical model we're considering is like the vertex models or Dimmer models. So basically we are considering models which have a local constraint. So I have my degrees of freedom on the links of a square lattice and some constraint for each vertex of my lattice. And we are just considering for now like a simple leasing variables on the lattice. And a wave function, so I have, what is the length? Okay. So I have my classical, my basis, my Hilbert space basis, which this are, as I said, the microstates. So I have basically a superposition over all the states of my basis. And these states are weighted with a Boltzmann factor, which is we have a Boltzmann factor. So we also have that normalization basically given by a classical partition function. Okay. So why are we interested in the entanglement entropy of this type of system? Well, this type of system from an entanglement point of view are particularly interesting because, well, okay, they can be computed from free energy of conformal field theories. Okay, so this gives us a convenient analytical tool to compute this. And also, well, besides as we expect an area law in this model, we also have subleading terms. And in particular, we have a subleading terms that grows with the logarithm of the bipartition of the system. The logarithm of the boundary. L here is the size of the boundary. And the particular thing that this subleading correction, they depend, for example, on the central charge, which is something that can basically identify the universality class of my critical point, and the shape of A and B, in the sense that it depends, for example, from the topology, both of the whole system and the partition, and also from basically sharp angles. So if there are like any singular points in the separation between the two partitions. And for example, here we have the three examples taken from this paper by Franklin and Moore, where we see that if we change the topology of the bipartition, we get some logarithmic correction with a factor of c over 4, while if we keep the topology but introduce some sharp angles, we have another factor in front of the logarithmic term. So this basically tells us that from a logarithmic term, we actually have information of like a global property of our system. And another thing, besides this logarithmic term, is also the presence of constant terms in entanglement scaling. And this constant term, from a conformal field theory point of view, are related to this Affleck-Ludwig boundary entropy and so on and so on. So this constant term should not be confused with the topological entanglement entropy, because here we are talking about of a simple bipartition, not a tripartition, and taking differences of the entropy. And yeah, so this depends, again, depends on basically on the low energy theory. So maybe here I should emphasize that when I say that something, in this case, depends on the conformal field theory describing my critical phase, it means that basically it depends on the universality class of our system. It doesn't depend on the macroscopical details. It only depends on the long wavelength behavior of our system. So this is why looking for this subleading constant is something important, because it tells us what is something like the scale invariant physics or macroscopic physics, or depending on how you want to put it. Okay. So the question that we asked and we wanted to try to solve is basically if the system size parity, so we are taking a system on a lattice, we are not taking a continuum system. If the system on a lattice depends on the parity of the size. So basically if the size is even or odd. Later it will be clear why we are looking at this. But already in like one-dimensional critical system, the answer is affirmative. So there are some effects that depends on low energy description already defined by Calabrese and company, and also some other paper that actually is like suggest if we have, for example, antiferromagnetic system with periodic boundary condition and odd size, this actually like modifies what is the phase diagram of these spin chains, for example. Okay, so if we want to basically to see if there are any effect of entanglement, but the method that I showed before, they depend on the basically on the action formulation of the system. We want some end on the replica trick. So we basically working with a continuum system, or like the macroscopic version of the scaling limit of a lattice system. Here we want to work directly with the lattice and try to use a replica-free method. And for the class of model that we are looking at. So in our case, actually, it has been found out that if we take our system living on a cylinder with a bipartition in the middle, there is a way actually to write exactly what is the Schmidt decomposition of the Roxer-Kivelson wave function. And this depends on the fact that we have a local constraint. So if we take our boundary between the two partitions, if we fix like a boundary, some boundary configuration, this constrains also what are the configuration allowed above and below the boundary. So basically this let us write a Schmidt decomposition which is a sum over all the possible boundary configuration. And for each boundary configuration, we have some practically a reduced Roxer-Kivelson wave function, but with some obviously imposed boundary condition, because it has to agree with this. So we arrive at this form here. And the interesting fact about this is that we have also a direct expression of what is the Schmidt eigenvalue. And the Schmidt eigenvalue here, the relevant thing is that is basically a ratio of partition function. So it's a ratio of classical quantity. Okay, so at the numerator, we have a partition function with some fixed boundary condition, which is DC, and the denominator is the partition function of the whole system. So we have a partition function, so we can go further. Some of you may know that basically a partition function can be written down basically as a discrete time evolution of a one-dimensional quantum system in imaginary time. Okay, so for this is basically related to the equivalency between two-dimensional statistical system and one-dimensional quantum system. So using these facts and taking the limits of the height of the cylinder that goes to infinity. So in this limit here, what dominates the transfer matrix is the ground state of the quantum Hamiltonian associated to this transfer matrix. So it is a quantum Hamiltonian of a one-dimensional system. And doing this limit, we basically arrive with this, I can argue, even simpler expression. So we have found that the Schmidt eigenvalues of the decomposition of the 2D quantum system can be computed as the probability of the ground state of a one-dimensional system living on the boundary over a given basis. This is the basis where the transfer matrix is expressed. So the computation of the entanglement entropy, then it reduces to the computation of the Shannon entropy over this discrete set of probability. And so not just the entanglement, the von Neumann entropy, but this is also for all the other Rényi entropy for any order, because we have a direct expression of these eigenvalues here, or probability here. And this is actually like a very convenient fact, because it allowed us to reduce basically a two-dimensional problem, computing the entanglement entropy of a two-dimensional system, to a one-dimensional problem, computing the Shannon entropy of just a one-dimensional system, which we can think about it as the quantum system living on the boundary. Okay, in our work we decided to focus on the case where the Rényi order goes to infinity, which is something that in literature sometimes referred to as mean entropy. One, because it's computationally easier, because we just need one probability. And second, this is where the effects of this size, this even or odd system size are much more evident. Okay, so we are focusing on the mean entropy, but we want to compute the mean entropy of what? So of what we have called like the quantum six-vertex model, in the sense that we are taking again, a Roxas-Kivers wave function built from the microstate of the six-vertex model. So for those who don't know what is a six-vertex model, it is actually like a well-known statistical models in two dimension, classical statistical model in two dimension, with binary degrees of freedom on the links, which can be visualized as arrows, and a simple rule for each vertex, which means that we must have the same number of arrows going in and the same number of arrows going out. And each vertex configuration can have its weight, basically. And the quantum version of it can also be thought about as a U1 lattice gauge theory. And this constraint basically corresponds to a Gauss law. So we are talking about a charge conservation for a Gauss law for each vertex of our model. And it is because this is a well-known two-dimensional statistical model, it is also well-known what is the quantum Hamiltonian associated to this model. And it is the spin 1/2 XXZ chain. So I have a one-dimensional chain, one-dimensional system, with interaction along all the three axes, but with only isotropy of the interaction on the XY plane, while we have an anisotropy in the Z direction. And the delta here, the anisotropy parameter, is directly related to the weights of the six-vertex model. Okay, so we are considering this spin 1/2 because we started with cylindrical geometry for our two-dimensional system. It means that we are considering XXZ chain with periodic boundary condition. Okay. So what are the properties of this chain that we are most interested in? Because we are talking about the critical wave function, we want to treat the spin chain in its critical phase. And luckily, it doesn't have like one single critical point, but actually it has like a whole continuous region in which is critical. And this region extends from -1 to 1, 1 included. This one included corresponded to the Bikety transition, and also it's the isotropic Heisenberg model. So all this region is critical. We don't care what happens outside of it. And also the delta equal 1 is included in this critical region. And what is the conformal field theory description of this critical phase? It's actually what is called compactified free boson inside the region. So a boson field is simply a scalar field, no? So it is a massless boson, so we don't have any mass term. So this is what makes this boson critical. Plus, we have also this compactification condition. So actually, the values of the boson field don't live on the real axis. So it doesn't take value on the whole real axis, but actually, we can think of taking values on a 5 minutes. Okay, on a circle with radius r. And this is a CFT with center charge equal to 1, and this is the expression for the compactification radius. Okay, so why this model? It has been established that because we want to evaluate the mean entropy, we must know what is the maximal state, so the state with the maximal entropy. And it has been established that it is a state it is a nil state. So it's an alternating configuration of up and down. And this can be very, very different if we are even size chain or the size chain. In the even size chain, the total magnetization is 0 and only have 2 possibilities for the new state. While if L is odd, we always have like a parallel pair living on this chain. And so there is like an extensive degeneracy of what is the maximal state. And so we suppose that this degeneracy must contribute in some way to this mean entropy. So to start this investigation, we first start to 2 specific points, this delta equal 1 alpha, delta equal 0, then try to generalize based on those results in a particular representation of the wave function. Okay, so for delta, I'm going to be very quick here. For delta equal 1 alpha, we basically use what is a particular conjecture that is exactly for our case. Yeah, exactly for our case. So by taking directly the data of the conjecture, we can compute the mean entropy, and we find that there is indeed a logarithmic correction with in front of a coefficient 1/3. Then going to the delta equal 0, this is a special point for the XZ because it corresponds to a free fermion point. So for free fermion, we can compute this probability through a slate determinant. So by comparing the slate determinant for an even case and the odd case, we find that there is indeed a logarithmic term. There is a sublinear logarithmic term with a different coefficient this time, which is 1/4 and not 1/3. So there must be some dependence on the anisotropy parameter. But in order to evaluate this, we need some kind of representation of the wave function. And for this case, instead of setting up, I don't know, Bertin-Ansatz equation, we decided to use the infinite MPS ansatz. So it's an MPS for the limit case where the bond dimension is infinite. So we substitute the financial matrix with vertex operator. It has luckily just one variational parameter, and it has at the end a simple expression for the wave function, for the components of the wave function with its normalization. So this looks pretty familiar because it's actually like very similar to the slate determinant. And by Sirac and Sierra, it has been established what is the relation between the variational parameter alpha and delta. So we see for delta equal 1 alpha, we have exactly 1/3. For delta equal 0, we have exactly 1/4. So it is actually our cases. So by using this data, by using basically the IMPS and the result for the slate determinant, we can actually prove that the difference in entropy between the odd and even case contains a subleading term that grows as a logarithm with a global coefficient alpha that depends on the anisotropy parameter. And this dependence is not random because it's also related to the compactification radius or the Luttinger parameter, or in general the exponent of spin-spin correlation function. So we can also establish a sort of CFT heuristic argument. Basically, the idea is identify the odd ground state not as a simple CFT vacuum, but a vacuum with excitation living on it. So by then writing down this as inner product, evaluating this inner product, basically these logarithmic terms derives from properties of a one-body correlation function. And so the field that created this spin excitation has exactly half the coefficient in front of our logarithmic correction. So it has actually like a connection to the low energy description of our model, of our CFT. And so yeah, these are the conclusion. So So the geometric fluctuation actually contribute to the entropy, and this is the entropy contribution due to a moving spin on a rounded boundary, which does not happen when the size is even. And the log term is actually directly related to the underlying CFT. So the possible outputs are like what happens when the order of the Rényi entropy is not infinite, and what happens when we take theories that have central charge different from 1. So thank you for your time.
Thank you, Suni. Questions? I do have one. Yeah? Actually, nowadays there's quite a lot of discussion about talking about these oddities, these parity effects,
yes,
in relating them to these non-invertible symmetries and to the dualities. So how does that?
I heard about this non-invertible symmetry or generalized symmetry, and I'm still not sure what is the relation with the oddities. So this is something that okay.
Okay.
Maybe you can tell me something later.
Not much, but
okay.
I can give you some references. That's it.
Okay.
Okay, if there's nothing more, I think we should thank Suni again and Tobias.